Hi, this is Dr. John Bergduff, and this is the second of two videos on probability. There's a separate video on general concepts of probability and empirical probability. Before we begin talking about theoretical probability, let's review some words. First of all, probability is a number that indicates how likely a specific event is to occur for a given random phenomenon. How do you associate a number with an event to indicate how likely that event is to occur? Some other terminology. We talked about sample space. Sample space is the set of all possible outcomes for a given random phenomenon. An event is a collection of outcomes that you are particularly interested in. And the symbol N of A that you see right here is used for any kind of set, whether it's a set of outcomes or a set of anything else, and it represents the number of elements in that set. Now, what makes the problems we're going to look at in this video special is that they come from sample spaces where every outcome is equally likely. This is not something you always know to be true. If you don't know if it's true, then your only chance is to run an experiment and use the idea of empirical probability. But if the outcomes are, you believe, equally likely, then you can calculate theoretical probability. And here is the formula. The theoretical probability of an event, E, chosen from a sample space S, in which all the outcomes are equally likely, is given by this formula right here. The probability of E equals the number of elements in E divided by the number of elements in S, and more colloquially, it's the number of outcomes in the event you're interested in over the total number of all possible outcomes. Let's explore what this means. Here's some simple examples. If one die is thrown, what is the probability that you will roll an even number? Now, the assumption here is that all outcomes are equally likely. If you have a fair die and you roll it, getting a 1 or getting a 5 or getting a 3 should all be equally likely outcomes. What is the probability of rolling an even number? To make sense of this, what you do is you think about what is the sample space. The sample space is the collection of all possible outcomes. And if I roll a die, the possible outcomes are 1, 2, 3, 4, 5, and 6. We're interested in rolling an even number. The event of rolling an even number is 2, 4, 6. And according to the formula that we saw on the previous slide, the probability of the event is the number of outcomes in the event you're interested in divided by the total number of all possible outcomes. We're not looking at the outcomes themselves, but how many there are. So if I was interested in the probability of E, what I would notice is what I'm interested in, the number of outcomes I'm interested in is 3, and the number of total outcomes that I have is 6. 3 out of the 6 outcomes are even, so the probability is 3 over 6, which reduces to 1/2. And if we think about that, it makes sense. If we have a fair die, we should get an even number about half of the time. That is theoretical probability. Here's another example. If a coin is tossed twice in a row, what is the probability of landing on heads both times? So to use the definition of theoretical probability, you have to understand both the sample space and the event, and in particular, how many outcomes are in each. So let's think a little bit about what the sample space is for this problem, the set of all possible outcomes. You're you're tossing a coin twice in a row. What are the possible outcomes? Well, I'm going to represent heads with H and tails with T. You could get heads both times, heads followed by heads. You could get heads followed by tails, tails followed by heads, or you could get two tails. What's important here is the number of outcomes in the sample space, which is 4. This is all possible outcomes. The outcomes that you are interested in is the single outcome where you get heads both times. So the probability of the event, the number of outcomes that you care about, that you're interested in, and there's only one, over the total number of all possible outcomes, and there's 4, the probability is 1/4. So I hope that makes sense. Let's look at some examples that get a little bit more involved using cards. So one card is picked from a standard deck. What is the probability that it is a face card? What I have drawn here is the complete sample space of all possible cards that you could draw. 4 suits, 13 cards in each suit. So if I were to count up exactly how many different cards there would be 4 times 13, and that would give you a sample space that has a total of 52 cards. What we're interested in, the outcomes we're interested in are the face cards. Those are over here. And there are 12 of them. 12 outcomes that you're interested in out of 52 possible cards. So the probability here is, I'm kind of low on space, 12 outcomes that you're interested in out of 52 cards. We can reduce that if we choose, noticing that 4 divides into both 12 and 52. That reduces to 3/13. Does that make sense? Well, if we look at any suit, 3 of the 13 cards in that suit are face cards, and that's true for every suit, so it kind of makes sense that we should get a face card 3/13 of the time. I need to clean this up just a little bit so we can look at the next example. One card is picked, example 4, one card is picked from a standard deck. What is the probability that it is a 7 or a club? The sample space is the same size, 52 cards. Let's look at the particular event we're interested in. And we're going to do that simply by looking at the sample space and picking them out. We are looking for either getting a 7, that would be any of these 4, or a club. You first might think, oh, I add 4 and 13, but if you do that, be careful you don't count the 7 of clubs twice. If we count all the outcomes here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We already counted the 7 of clubs, 14, 15, 16. 16 cards are of the event you're interested in. Out of 52 total cards, number on top is the number of cards in the event you're interested in. The number on the bottom is the number of cards or outcomes in total. 16/52. Again, both of those numbers happen to be divisible by 4. This would reduce to 4/13. The probability is 4/13. And that comes directly from the formula. Number of elements in the event, over number of elements in the sample space. Just a couple more examples. 2 dice are thrown. Find the probability of rolling a sum of 8. So for any probability problem, if you're using theoretical probability, you have to know what the sample space looks like. And I have drawn that here for you. We are rolling two dice. We'll say one is gray and one is white. This picture represents every possible outcome. This is an outcome, for example, rolling a 1 followed by a 1. If we count the outcomes, there are a total of 36. So using my formula, the number of outcomes in my event over the number of outcomes in the sample space, the number in the denominator is going to be, the number in the denominator is the total number of possible outcomes. That's 36. And now we just have to count which outcomes would give me a sum of 8. And we're simply going to look. This one does 6 and 2. So does 5 and 3. 4 and 4. 5 and 3. 2 and 6. Just picking from the sample space, all of these outcomes would result in a sum of 8, and there are 1, 2, 3, 4, 5 of them. 5 over 36. 5 outcomes we're interested in, 36 outcomes total. 5 over 36. That fraction doesn't reduce. There's no common factor in there. Okay, hope that makes sense. Let me clean that up a little bit before I do the next example based on the same sample space. Find the probability of rolling an even number on the gray die. So again, we can just look at the sample space and pick out the outcomes we're interested in. An even number on the gray die, well, all of these, the gray die is a 2, that's even. All of these, the gray die is a 4, that's even. All of these, the gray die is a 6. How many outcomes is that? Well, 6 in each row, 1, 2, 3, 4, 5, 6, 3 rows. We are interested in 18 outcomes out of the 36 possible outcomes, n of e over n of s, and that reduces to 1/2. Now, if we compare the two probabilities we've seen so far, 5/36 is less than 1/2, and remembering what outcomes those were, there are fewer outcomes. So it would seem likely that it would be less likely that you'd roll a sum of 8 than you roll an even on the gray die. The smaller the fraction, the smaller the probability, the less likely the event. One more example here before we draw some conclusions. Find the probability of rolling a 13. A sum of 13, rather. So let's go back a little bit and locate all outcomes that give me a sum of 13. Well, I think I've got a problem there because the biggest numbers on the die are 6, and if I roll 2 6s, that only gives me a sum of 12. There are no outcomes that give you a sum of 13 out of the 36 possible outcomes. That means the probability is 0. And that leads us to this sort of concluding observation here. Notice that all the fractions we've seen so far lie between 0 and 1 inclusive. That means it could be 0 or it could be 1. A probability of 0, like we just saw, indicates an impossible event, like rolling a sum of 13. A probability of 1 indicates that the event is certain. So if I were to ask, for example, what's the probability of rolling a sum less than 100, all of these outcomes would give you a sum less than 100. So it would be 36 over 36, and that would be 1. The probability of a probability of 1 indicates that an event is certain. I hope that helps.